Has the well-established question of whether our species is extraordinary in the universe at last been addressed? We may be drawing nearer to a game-changing finding, thanks to the James Webb Space Telescope presenting K2-18b, a distant exoplanet that has recently become a focal point in the field of astrobiology.
Why?
Its atmosphere contains an anomaly that the James Webb Telescope discovered, which might indicate the presence of life. The molecules that make up water vapor, methane, and the very rare compound dimethyl sulfide aren't entirely random. Perhaps these are the biomarkers that have been puzzling researchers for so long. Does this mean that extraterrestrial life truly exists? Our new guardian of the galaxy, the James Webb Space Telescope, JWST, is equipped with the most cutting-edge space hardware ever constructed. Its purpose is to peer into the unknown and potentially redefine our understanding of existence. The enigmatic universe of K2-18b could be something we are now ready to explore. We rely on telescopes and other technological marvels to sharpen our understanding of the universe as we journey further into space in search of answers to mysteries that have confounded humanity for centuries. Among these, the James Webb Space Telescope stands out. We owe an immense debt of gratitude to the Hubble Space Telescope for decades of providing us with stunning, informative images of the universe. Still, even Hubble has its limitations. Enter the James Webb Space Telescope, a telescope whose mission is to expand our understanding of the universe through the power of light. The JWST cooling shield technology is among its most remarkable features. The size of a tennis court, this intricate technical marvel blocks the heat of the sun, earth, and moon, making it far from a standard sunshade. Why is this so crucial? The telescope can be cooled to extremely low temperatures, making it more sensitive to faint infrared signals emitted by faraway stars. Exoplanets like K2-18b can only be studied using infrared observations. Space dust can block or scatter visible light, but infrared waves can pass right through it, allowing for much clearer and more detailed images. Infrared observations made possible by JWST represent not just an achievement but a game-changer in our understanding of distant planets. What new information might we uncover as our focus turns to K2-18b? This rocky exoplanet, located 124 light-years away in the constellation Leo, orbits in its star's habitable zone, often called the Goldilocks zone, where temperatures are just right for liquid water to exist. K2-18b, however, is unlike other exoplanets in similar orbits. Scientifically, it is classified as a high-sea world, not your typical rocky planet. The discovery of potentially habitable worlds with an oceanic surface and an atmosphere rich in hydrogen marks a new chapter in the search for alien life. These planets offer conditions similar to Earth's hydrothermal vents, known to host diverse ecosystems. New data regarding K2-18b's atmosphere has been revealed by the James Webb Space Telescope's recent studies. The atmosphere of this faraway planet contains various gases and elements that might support life, or at least life as we know it. These include water vapor, methane, and possibly even dimethyl sulfide. The scientific community is abuzz with excitement, speculation, and hope about what these findings could mean for astrobiology and the search for extraterrestrial life. The unique atmospheric composition of this high-sea world raises the intriguing possibility that it holds the key to understanding life beyond Earth. What does the future of astrobiology hold? Considering its exceptional conditions, one of the most challenging and potentially rewarding aspects of exploring extraterrestrial planets is learning about their atmospheres. K2-18b's unusual atmospheric makeup and unique position in the habitable zone make it a compelling case study of how exciting and fruitful these kinds of investigations can be. Its atmosphere differs greatly from Earth's, which consists of trace gases, nitrogen, and oxygen. The hydrogen-dominated atmosphere of K2-18b is rich with scientific mysteries, containing trace amounts of water vapor, methane, and even dimethyl sulfide. Methane and water vapor in its atmosphere point to an environment that would challenge conventional notions of habitability. However, extremophiles on Earth, such as those thriving in hydrothermal vents or highly acidic lakes, remind us that life can adapt to conditions once thought inhospitable. The next steps in studying K2-18b involve detailed atmospheric modeling and further spectroscopic analysis. Scientists aim to confirm the presence of dimethyl sulfide, DMS, a compound typically produced by biological processes on Earth. If DMS is indeed present, it would provide compelling evidence for potential life beyond Earth. Understanding the planet's ocean dynamics, geological activity, and atmospheric composition will be crucial in determining whether K2-18b is truly habitable or merely intriguing from a chemical standpoint. The discovery of dimethyl sulfide or other unexpected biomarkers would not only deepen our understanding of K2-18b, but also redefine our search for extraterrestrial life. Instead of focusing solely on Earth-like planets, we may need to expand our horizons to include worlds with diverse atmospheric compositions and unconventional habitability criteria. This broader perspective could open the door to identifying a wide variety of exoplanets capable of supporting life. Planets with hydrogen-rich atmospheres, ocean worlds beneath icy crusts, or even moons orbiting gas giants may all emerge as viable candidates in the search for alien ecosystems. The tools and techniques pioneered by the James Webb Space Telescope will play a vital role in exploring these possibilities. The implications of finding life on K2-18b or any other exoplanet are profound. Such a discovery would not only answer the age-old question of whether we are alone in the universe but also force us to rethink our place within it. The realization that life can thrive in vastly different conditions would expand our understanding of biology, evolution, and the adaptability of life itself. Additionally, the confirmation of extraterrestrial life would have philosophical, cultural, and even practical implications. It could inspire a new era of scientific collaboration and innovation as humanity unites in its quest to understand and communicate with life beyond Earth. As we continue to investigate K2-18b, it's essential to approach the search for life with both excitement and caution. The process of interpreting atmospheric data is complex, and false positives can arise from non-biological processes. Therefore, the scientific community must proceed rigorously, building evidence piece by piece to construct a compelling case for the presence of life. In the meantime, K2-18b serves as a reminder of the boundless possibilities that await us in the cosmos. Each new discovery fuels our curiosity and determination to explore, pushing the boundaries of human knowledge. Whether or not K2-18b ultimately reveals signs of life, its study represents a milestone in our journey to understand the universe and our place within it. With the James Webb Space Telescope leading the way, humanity stands on the brink of answering one of its most profound questions. As we peer deeper into the cosmos, we may discover that life, in its infinite forms, is not confined to Earth but is instead a fundamental part of the universe's grand design. Dimethyl sulfide, DMS, could be present in K2-18b's atmosphere, which is one of the most intriguing aspects of studying it. This chemical, which could be a biosignature, is regularly made by phytoplankton on Earth. Does its existence on K2-18b and other exoplanets suggest the possibility of life? After being oxidized in the atmosphere, DMS contributes to cloud formation in Earth's oceans. The discovery of life beyond Earth may hinge on its existence in an exoplanet's atmosphere. Similar to K2-18b, we are still in the process of testing K2-18b for DMS. Nevertheless, it has also ignited controversy, as is typical with any revolutionary finding. What DMS means for K2-18b is a contentious topic among scientists. Some see it as a promising biosignature candidate, while others point out that molecules with comparable structures can be generated by abiotic processes as well. The difficulty and complexity of deciphering extraterrestrial data are highlighted by this discussion. Skepticism has frequently greeted astronomical discoveries throughout history. At first, many people didn't believe Galileo when he said that Jupiter had satellites. There was also hesitancy when the first exoplanet was discovered in 1995. The importance of skepticism in the scientific process is underscored by these historical examples. No one chemical or observation is crucial to the hunt for alien life. Researchers are on the lookout for biosignatures that, when combined, might provide strong proof of life. Is it possible that DMS, along with other biosignatures such as methane and water vapor, forms a bigger picture? Until further information is gathered, the discussion is likely to go on. The proof that DMS is a genuine biosignature may be forthcoming from future missions with even more sensitive instruments, provided that technology continues to progress. Does DMS hold the secret to finding extraterrestrial life, or is it just a diversion? Regardless of your stance, the ongoing discussion highlights how science is dynamic. Our knowledge of K2-18b and other exoplanets has been greatly enhanced by the James Webb Space Telescope, JWST, but this is only the beginning of space exploration, a long and winding road. How will technology develop in the future, and what lies beyond this massive endeavor to broaden our understanding of the universe? Another revolutionary project is the Extremely Large Telescope, ELT, which is expected to be completed by 2025. The world's largest near-infrared optical telescope, with a main mirror diameter of 128 feet, will soon be revealed. Biosignatures found by the James Webb Space Telescope may be confirmed or disproven by its unparalleled sensitivity. Findings from the James Webb could also be supplemented by data from another forthcoming mission, the Large UV Optical Infrared Surveyor, LUAR, with its versatile operating wavelengths. LUAR has the ability to acquire direct images of exoplanets and conduct more in-depth atmosphere assessments. Propulsion technology advancements are crucial as we aim for farther-away exoplanets. Ion propulsion and other possible approaches, including antimatter propulsion, could allow probes to explore exoplanets within a human lifetime by substantially reducing travel times. We have an earlier video that discusses the potential and difficulties of interstellar travel. We should pause to think about the philosophical ramifications of our search for alien life as we are on the cusp of potentially game-changing discoveries. How does this journey impact our comprehension of the universe, and what kinds of concerns does it raise about what lies ahead? A new mystery is the function of red dwarfs throughout the cosmos. These frequently ignored stars are the potential birthplaces of all life. They are intriguing hosts for planets that could support life because of their stability and durability. We would be confirming the presence of life beyond Earth and suggesting that the basic building blocks of life are more universal than we formerly assumed. If we found extraterrestrial plankton or other kinds of life on planets like K2-18b, what mysteries will the coming decade unveil? Would we find more complicated puzzles that test our cosmic knowledge, or would we prove the presence of alien life? As we continue to push the boundaries of space exploration, the discovery of exoplanets like K2-18b opens up new avenues for understanding the vastness and diversity of potential habitats across the universe. The fact that we are now able to study exoplanet atmospheres in such detail marks a turning point in our search for extraterrestrial life. The combination of advanced instruments, such as the James Webb Space Telescope, JWST, and future missions like LUAR and ELT will only enhance our ability to identify and analyze distant planets, possibly leading to the discovery of more planets with conditions suitable for life. These advancements in space exploration not only provide exciting prospects for the search for life, but also help refine our understanding of the conditions that allow life to thrive. Researchers are looking beyond Earth-like conditions, expanding the range of environments where life might exist. For instance, while we often associate habitability with planets that possess a breathable atmosphere and liquid water on their surface, planets like K2-18b challenge this conventional thinking by introducing the possibility that life could exist in extreme conditions previously considered inhospitable. Furthermore, the study of exoplanets like K2-18b encourages a broader view of what constitutes a life-supporting environment. While Earth-centric theories of life primarily focus on planets with a stable temperate climate, the discovery of extremophiles on Earth, organisms that can survive in environments ranging from boiling hot springs to extreme acidity, has forced scientists to reconsider what is necessary for life to flourish. K2-18b, with its hydrogen-rich atmosphere, is the ideal candidate for further research into this expanding understanding of life's potential. These discoveries also prompt scientists to examine the wider implications of their research as they raise questions about the fundamental nature of life itself. The possibility of life on other planets could have profound implications for humanity's view of its place in the cosmos. It might challenge the long-held assumption that Earth is the only cradle of life in the universe. While the discovery of extraterrestrial life would be revolutionary, it could also bring new ethical considerations, particularly regarding how we interact with and preserve alien ecosystems. The idea of encountering life beyond Earth also raises the question of how we might recognize and communicate with other life forms. Would extraterrestrial life be intelligent, or might it take forms far different from anything we can imagine? As we venture further into the unknown, it becomes clear that the search for life is not just about confirming the existence of alien organisms. It is about pushing the boundaries of knowledge and testing the limits of human curiosity, and challenging our understanding of biology, evolution, and the nature of life itself. The ongoing study of exoplanets like K2-18b, coupled with the revolutionary capabilities of instruments such as the James Webb Space Telescope, JWST, offers a new era in the search for extraterrestrial life. The telescope's ability to detect atmospheric molecules, including methane, water vapor, and potentially dimethyl sulfide, DMS, is leading us closer to unraveling the cosmic mystery of whether life exists beyond Earth. However, as promising as these findings are, they also raise critical scientific and philosophical questions. If life is discovered elsewhere, it would not only transform our understanding of biology but also spark debates about the origins and universality of life in the cosmos. The presence of biomolecules like methane on K2-18b does not guarantee life, as non-biological processes could also produce these chemicals. The scientific community must approach these findings with caution, rigorously testing and analyzing all possible explanations before making any conclusions about the presence of life. As the James Webb Space Telescope continues to exceed expectations, and as upcoming missions like the Extremely Large Telescope, ELT, and the Large UV Optical Infrared Surveyor, LUVR, come online, we will have more powerful tools at our disposal to probe the atmospheres of distant exoplanets. These advancements may lead to the identification of more potentially habitable planets, broadening our search for life beyond Earth. Additionally, breakthroughs in propulsion technologies, including ion propulsion and antimatter propulsion, could one day allow humanity to explore exoplanets within a human lifetime, taking us further into the depths of space. The study of red dwarf stars, once considered relatively unimportant, is gaining more